He did the mash. He did the monster mash. The monster mash.
We've talked about how to do curvilinear regression, or the idea of it. Let's see an actual example. So we're going to start by looking at the processor data, which I'm going to call process because I'm too lazy to do that last OR. And this data set has a bunch of different processors with how old the processor is and how fast it is. So let's take a look at what this picture looks like. And we can see that as the processors get older, they tend to wear down. Apparently their age starts at 1 year because it takes a year for it to get shipped, or whatever else sounds realistic for a made-up data set. Let's do regression, and because we just finished talking about curves, as you look at this, you might very well notice the curvature here. But let's pretend we didn't notice that, because you might say to yourself, okay, it looks like a straight line would be fine. So if we didn't know that we needed a curve, we would fit just speed based on age, and we would get some residuals like this. Let's take a look. Do you notice it? Do you notice the curve here? It looks kind of rainbow shaped. It's distinct enough that even R noticed it and drew a little red line to say there's kind of a curve here. But this is going to be the only real place that it shows up. The QQ plot looks okay. I like that. That's supposed to follow the line, and it does. Now, the next plot is going to go back to this one, and it's going to fold it right along this zero line. So these small dots are going to come up here. Those low dots are going to come up here, which means it's going to actually look pretty good. And if I press enter, there it is. This looks fine. And sometimes that folding trick will bring up patterns that you might not have noticed before. In this case, it actually just masks patterns. And the leverage plot says there's no particular data point that's causing problems. We can't even see those red dashed lines that would indicate that there was a data point that was out of whack. So this very first residual plot really is critically important. And I see a curve there. And I want you to notice something. If I go look at the summary, I've got a decently good R-squared, 0.7433. That might make me feel like I've got a good model. But the fact that the residuals show a curve means we have not modeled this correctly. And they're showing a curve because there is a slight curve in the data, so we should improve it by adding that curve in. And for this video, I want the curve to be a quadratic. It's made up data and I made it with a quadratic, so this is actually going to turn out well. But in the next video, we're going to say what other curves might go well, and could some of those be equally valid? So let's do this the slow way, by creating an actual age squared variable. And you should be shaking your head saying, isn't there an easier way to do this? Well, yes, there is, and we'll do that in a second. But this is my pattern. I want to show you slowly what's going on. So there I actually squared age, and I'm going to column bind it to my process so that when I look at my process, I have age, and now I have age squared. And the y variable is stuck in between the two right here. Speed is what we're trying to predict. So with both of these, I can do a quadratic model. Now, you might be tempted, at least I would have, to start with this. And I said, don't start with this because it's not versatile. And that's if we did just a model with speed being predicted by age squared. And here's why that doesn't work. If your model only has the intercept and the x squared terms, these are the kinds of graphs you can get. 2x squared, 3x squared, 4x squared, 5x squared. And what that does is it takes your curve and makes it more steep. But it locks it here against the y-axis. You could change the y-intercept, 1, 2, 3, 4, and what that would do is shift these up or down. You could change the slope on x squared negative, which would flip them around, but you're still stuck along this axis of being where your curve is. You couldn't, for example, draw a curve like this, where the vertex of the parabola is off the y-axis. You can't get that with this kind of curve. And that's why I said right here, it's not versatile enough to cover all the types of models we might want. So let's run this and look at our summary. Here we have our intercept and that coefficient on the slope. And let me draw how that looks on the picture. Going to start with the original picture, that's what we have, and let's make some ages that we can use for our prediction. They go from 1 to 6. I did 1,000 just so that I have lots of dots to try to draw this curve. And then my prediction equation for the speed is going to be 103.72, and then the negative 1.88 times those predicted age values squared. And let's draw what that looks like with red, because that's my favorite color. Look at that. It's not bad, but is it really fitting the line as well as it could? Notice that right here it tends to have bent up more than it should. Why? Because it has to hit the vertex of the parabola at the 0 mark, which 0 would be, let's see, 2, 1, 0. 0 would be somewhere over here. So that has to be the apex of the parabola, and so it can't quite bend down the way it should. If you looked at the value of 1, would we really predict up this high? I would say it should be a little bit lower right there. Let's see what the residuals have to say. The first main residual, do you see a pattern? And there's a slight bend in there. If you look at that red line, R is saying there's a little bit of a curve. It's not super strong. That looks great, still looks great. Leverage plot says no data points off. So you could think that you have a good model, but if we include that X term, we're actually going to improve it. So I'm going to steal what we had before, and here where I have age squared, I'm going to also include age. And you'll notice in the summary, I now have age and age squared. So if I want to draw what it's doing, I still use the same ages, but this prediction equation is now going to change. It's 95.6581, 5.3070 times age hat, because we're using hats to say this is something we've predicted. And that negative 2 times age hat squared. So this will give us a slightly different regression line. Ooh, look at that. What's the difference? This part doesn't look so different. But remember before how it was curving up way too high here, and now it's bent down? I hope that you're not like watching this on your iPhone where you can't see the difference. But it's bent down a little bit better. I would say this looks like it's following the data better. Do the residuals agree? Oh, look at that line. Before there was a slight bend to it. It was actually hard to see, but now it definitely looks straight. QQ plot looks straight. Okay, that looks good. Of course, that looks good. Now I'm going to use one more thing to test. Did I really need that X value in there? Fix fit. Let's look at the p-values. And the p-value for the X is 1 times 10 to the negative 0.05. So let's see, scientific notation. That means there were 4 zeros. 0.00001. That's a very small p-value. Yes, this is useful. If you didn't think you needed it, you would have missed something that's actually helpful to your model. Now, we did that by actually creating this variable called age squared. There's obviously an easier way to do that in R, but I want to start by showing you a bad way. And I start with this because this is how I would have thought it would work. I'm going to try to predict speed based on age, and then just plus an age squared in there. But this caret term in the LM statement is interpreted as a different meaning. And so if I run this and then do a summary of the fit, I can see only age showed up. It didn't have age squared. So what I need to do is to use this special I command to tell it to interpret age squared correctly. And people who are experts on R would probably scream, that I stands for inhibit. You know what? If you know R well enough to know that, then you just skip the video and do the homework. We're going to say I is for interpret it correctly, and that is how the age squared variable is going to be understood. And if I run this with a summary, I get both age and age squared. And notice these are not the exact same values we had before. Oh, good, they sure are. Okay, so we've done the exact same thing, and this is going to be the notation we're going to use. And so if you have some weird function that you're doing, put it in I, and it's going to work fine. There is one exception to that, which is the log, and that's one of the last things we're going to do in this class because logs are so cool and valuable. The LM statement treats them differently, and so will we. Let me real quick emphasize something that you can probably already guess. If you put age squared in, that does not mean you're going to get age in the model automatically. Same as when we had age and age squared as our own variables that we made. It'll have age squared, but not age. Some people would argue that R should have it designed that way, but it doesn't. Okay, that's enough of an introduction that you can see how it's going to work. In the next video, let's try a whole bunch of different functions and see, based on the original curve, what things might fit well, and how would we decide between them.